Okay, so hello everyone. So before we start, I want to clarify a few things, some logistics. So in week one, I uploaded some slides. We were not able to go through all the slides, but I gave you the general idea about the correlation and the important things that you need to know about the correlation. Now, for the rest of the slides, feel free to go through them. These will give you some extra information regarding the material that we've covered. One important thing is that I also have a take-home activity. So we did one activity with a number of crimes in Chicago, but there is another example, another data set about the Capitol Hills, the houses in Capitol Hills I think in Seattle. This one, you can do it as a practice, okay? It's like another activity where you can try to do the scatter plots, do the correlations. Feel free to practice. I upload those two questions so you can get some more practice regarding those materials. Now, I also provide you the textbook that I'm following. So you can see now in our folder for week one, I have a Word document and I'm giving you the textbook that I'm following. Feel free, if you want to buy it, it's an interesting book where you can see some more discussion on the topics that we're covering. Another thing is, if you want to practice using the data sets that I'm giving you, I suggest you download the data set and then you do the analysis, okay? Because once you access it, if you do the analysis, then the next person will be able to see your analysis. And we don't want to make any changes to the data sets. So first, download the data sets on your laptop, on your computer, and then do the analysis that you want to do. Okay, another thing is that I upload, sometimes I will be uploading some papers that will be of interest. So I feel that these papers are related to what we are doing and will give you some, maybe another perspective or some more information regarding the material. Again, feel free to go through those papers. So those papers and also the textbook will give you a little bit, let's say, more discussion on the topics that we'll be covering. Okay, any questions on the things that we've covered last time? Or anything that you want to clarify? No? Okay, from online, anyone that has any questions?
I think a question.
But where can we read the question?
Let me see.
Maybe
I think you can look
maybe
there.
more, yeah. Chat.
Yeah.
Yeah, okay.
Here we go.
No, it's okay. Yeah, it's from
Okay.
before. Okay, so that's good. Now, in this week, we're gonna cover topics regarding the linear regression. I briefly gave you an idea last week, but today you're gonna give some more details, formally define what we mean by linear regression. We're gonna see what it is and more, let's say, the details, and we're gonna see how can you use Excel to fit, let's say, the linear regression, and then the second part will be regarding the statistical inference. So we're gonna try to talk about statistical inference in more giving you the intuition and a high-level discussion about, because the statistical inference, we really require a lot of time to get into the details, but I'm going to try to give you a general idea what's the purpose of the statistical inference and how we think, let's say, before conducting the statistical inference. Okay, now let's see. So last time, we define what we mean by the correlation, right? So we said the correlation is telling us the extent at which two features of the world, we call the variables, we call those features of the world variables. So the correlation is giving us an idea how those features of the world, at what extent those features of the world tend to occur together or not. And then we talk about some of the uses of the correlation. We said, we can use the correlation to describe the relationship between the two variables. We can use the correlation if we want to go one step ahead to, let's say, not just describe, but also be able to forecast and predict about some maybe new members, some new samples, some new members of the population. And then we said we can also do talk about causal inference. That's the hardest part, talking about causational relationship between the variables. Then we also talk about different ways to measure the correlation. We talk about the covariance. Okay, the covariance, we said it's a measure of the correlation, but it's affected by the magnitude of the variables. So we should usually avoid using the covariance. Instead, we prefer the correlation coefficients, where they standardize the magnitude to give us an idea. And then we also talk very briefly about the slope of the regression line. This was giving you, let's say, the rate of change. We're going to talk about the slope more in today's lecture. Now, before we get into today's class, where, as I said, today's class is about the linear regression, which is the most common and most useful way to characterize, let's say, the relationship between two variables. So we don't just want to describe, but I also want to say something more. Okay, so I want to be able to characterize the relationship between the variables. I want to make one comment. So last class, we're talking about the correlation, right? And I defined the correlation, the extent at which two features of the words tend to occur together or not. If we want precise, we need to get into that discussion of what is a correlation, what is association, and what is the independence. So these are like kind of similar topics in statistics, but not exactly the same. So for the people that maybe they look some other resources, I want to mention that association is more like a general definition, in the sense like I'm looking the relationship between any kind of variables. If we're talking about correlations, we're talking specifically for quantitative variables. So usually when I want to see the relationship between two quantitative variables, we're going to talk about correlations, okay? So I know in everyday language we use association, independence, and maybe correlation, interchangeably, but I want to make that distinction, okay? So association is more like a more general term when I'm looking at the relationship between any variables. When I talk about a correlation, we talk about the relationship between two quantitative variables, okay? So that's the comment that I wanted to make about the correlation. And now let's see. Let's go back in our data set. That's the crime versus the temperature. That's a data set from Chicago, 2018. And in that scenario, in that data set, we wanted to find what's the relationship between the number of reported crimes and the temperature, let's say, in Chicago. I want to remind you to explore that relationship. We created first a scatter plot. Let me remind you again, what is a scatter plot? So on the x-axis, you can see the temperature. On the y-axis, you have the values for the reported crimes. Now, each one of those dots represent a day in a year. And for each day, I have information about the temperature and the reported crimes, right? So if I want to explore the relationship between these two variables, first of all, usually a nice way is to start with some visualization to get a sense about that relationship. Before, let's say, we get into some modeling, some linear regression. Can someone remind me what we said about the relationship between the temperature and the reported crimes? What were some observations that we made in this specific data set? Yes?
Strong positive correlation?
So there is a strong positive correlation, okay? So you see that upward trend, okay, right? It's, okay, you said strong because did we calculate the correlation coefficient?
No.
But you can see that the data points, right? Yeah. They are closely together, okay? So these may be like, more like maybe strong correlation between the variables. Can someone online tell me, did we talk about the format? Is it a linear? Is it curve? So what's the relationship? Yeah, so see some people said positively correlated. Are we talking about a linear relationship? Is it a curve? Okay, so linear, yes. So we see the rate of change. So as I'm changing the temperature, I see kind of constant rate of change for the reported number of crimes. So it's roughly speaking, let's say, a positive linear relationship between the variables. Okay? Is that enough? Is that enough to just being able to describe the relationship between the variables? In a lot of cases, this may not be enough. We may want to go one step ahead and be able to, summarize the relationship. Not just describe, it's a positive, it's linear, but I want to be able to summarize the relationship between the variables. And why we may need to summarize the relationship between the variables, okay, you have two purposes. The first one if we're able to summarize the relationship between the variables, of course we can also describe. Okay, we can say that's what you just mentioned, like a positive linear relationship between the variables. But most importantly, if we're able to summarize them, and how do we summarize them? Let's say maybe we can just fit some lines, some curves passing through the data sets. If we're able to summarize the data, then we should be able to use that line to forecast, to make predictions. So let's say if I'm able here to summarize the data with a straight line, then what I can do is for specific temperature, I can go and see what are the expected number of crimes for that specific temperature. So not only we're able to, let's say, describe, but also are able to predict and forecast, okay, about some new, maybe some temperatures that I don't have in the data set, and be able to see the number of reported crimes. Also, not only just predict, but using, if you decided that a straight line is suitable to summarize the data, you're looking at the slope of the linear regression. This will also help us to see the rate of change of the reported number of crimes. So the slope of the line will tell us if I increase the temperature by 1 unit, how much should I expect to see, how much increase should I expect to see for the reported number of crimes? Okay? So that fitting that straight line will really help us to go one step ahead in our data analysis. Now, before I define the regression model, or let's say the linear model, let me take a moment and talk about, let's say, the equation of a straight line in mathematics. Yeah? So first, let's focus on the blue boxes here, okay? Forget about all the others, just focus on those blue boxes. Now, I want to remind you that anytime I want to define the equation of the linear, of a straight line, right, in mathematics, we use that, that notation here. We say, let's say our y, let's say our value on the, let's say our, I guess, on the y-axis, it's equal to that alpha plus beta times x. So alpha was the y-intercept, is where the straight line passes through the y-intercept. And then I have beta. Beta was the slope. So the slope was telling us how steep basically is our straight line, right? Do you remember that equation from mathematics? Okay. So y equals to alpha plus beta times x. So let's say in our case, if I'm talking about my y is the crime, then I have the crime equals to alpha plus beta times the temperature. Our x is our temperature in this setting. Okay. Any questions regarding the mathematical equation? Y equals to alpha times plus beta times x. Alpha is the slope, is the intercept, y-intercept, beta is the slope. Now let's go and see in statistics, how do we think about the linear regression? Now, as you can see from the data set, so let's go in our data set. Here, if I want to use a straight line, you can see that not all the points are on exactly straight line, right? So I don't have all the points one after another following a straight line. There is that variation in the data set, okay? So because of that variation, because I don't have that perfect straight line, in statistics, for the linear regression, we're going to have our regular equation for the straight line, but we're going to have some error term. Okay? So what I'm saying is that the crime will be, okay, the value of the linear regression plus some error. Maybe sometimes it's a positive number, sometimes it's the negative, but it's some error in the linear regression. Okay? Because I don't have a perfect line, right? I don't have all the points passing through the straight line. So I have some error. So our regression line would be basically our y equals to alpha plus beta times xi plus that epsilon, that error term. Now the y, we're going to call them dependent variable. And what I mean by dependent is the one that I want to predict. Okay? In our scenario, I want to predict the number of crimes. So these will be our dependent variable. Okay? The temperature will be what we call the independent variable. That's the variable that I'm going to use to see how it affects my dependent variable. Okay? And in this case, I have the temperature as the independent variable. Okay? Now, the subscript here represent that we have, let's say refers to that particular observation. Let's say crime I equals to alpha plus beta, temperature I plus epsilon I. We're talking about a particular data point. These would be our data set. In a data set, I have many observations, right? I represents the particular value in our data set. Okay. Okay, so that's our equation. So the equation of the regression line would be the y equals to alpha plus beta times x plus that epsilon, right? Because I have that variation in our data set. Now, we can use the linear regression to make predictions. Okay? So, given a specific temperature, let's say in our scenario, if I give you a specific temperature, how can we predict? How can we predict? We can use our regression line to make the predictions. And our regression line was, let's say the crime equals to alpha, the y-intercept, plus the slope times the temperature in that specific, the given temperature. Okay? So I want to remind you, I have the data set. We're going to try to fit the line. The equation of the line will be the number of crimes equals to alpha plus beta times the temperature. And then I can use that line to make predictions. More generally, we're going to have that form here. So anytime we're talking about predictions, we're going to use that hat. So that's like the notation. So before I had the yi equals to alpha plus beta times xi plus epsilon. That was, let's say, the relationship, the theoretical model. But when we go in practice and be able to make predictions, then we're going to have the y hat. That's the predicted. That's not the actual value. That's not the actual number of crimes. That's our predicted. Based on the linear model, that's, let's say, the predicted number of crimes that you may get equals to the equation of the straight line that you decided for that specific scenario. Now, we're also going to talk about the residual. The residual is nothing else but the difference between the predicted value of the response and the observed value from the data. So, using the model, we're not doing a perfect job in predicting, in our scenario, the number of crimes. Then there should be a difference between the actual value of the number of crimes and our predicted number of crimes. Of course, we want that to be small, right? The smaller, let's say, the residual, the better job we're doing, right? That is more. So our prediction is closer to the actual value. But that's how we measure the error, let's say, that we made in the linear regression setting, and we're going to call it as a residual, and I'm going to denote it by the EI. Okay? For each one of the observations, I can define, let's say, the residual, the actual value minus the predicted value. Any questions regarding these ones? No? Everything is clear? But how can I choose the alpha and beta? So here, okay, I told you we have the, let's say, predicted crime equals to alpha plus beta times the temperature. But what is the value of alpha? What is the value of beta? And this is what we're going to do on the next slide. So on the next slide, we're going to talk about how can I choose the best available line. As you can imagine, choosing different values for alpha, different values for beta, it would change your line, right? It would maybe steeper, or changing the y-intercept, it would change the line. So how do we choose the best line? And what I mean by best line, I'm going to talk in a minute the details, but I want the line that summarizes the data the best. Now, let's see. Now let's assume that here I gave you some values for the alpha and the beta. Okay? So let's say in this setting, I'm using alpha to be 615, the beta to be the number 2. Okay? So if we want to be more precise actually, and I want to write something on the slide, Usually, we use that hat notation if we're talking about a specific values for, let's say, those parameters. Okay, you have the alpha and the beta, but if I calculate or find some values, usually we use those hat, like an estimate for the alpha and estimate for the beta. Now, this equation will be helpful in what sense? So here I had our data set. Let's say I choose alpha and I choose beta, and then I feed a line. Okay? What can you tell from that line? First of all, yes?
I was going to say whether or not the correlation is positive or negative.
Okay. Using the line, you get an idea of the, let's say, the direction of the relationship. Yes?
Yeah, like the vertical line, so the residuals, right?
Okay, so these are the residuals, yes, and we're going to talk in a minute about the residuals and why it is important to look at the residuals. I can also see that, you know, the alpha is 650, so I'm expecting that the y-intercept will be at the 650, right? So, and the beta is the slope, so I get an idea of, let's say, if I increase the temperature by 1 unit, I'm expecting an increase in the number of crimes by 2. Right? So we still, that's not the best line, but still we can get some information regarding that line. Now let me talk about what is, let's say, the logic behind finding the best available line that can be passed through the data points. So let's say we have a line, so that's one example. And then what I'm gonna do is, I'm gonna calculate all the residuals, all the errors, right? So from this one, let's say from the data point to the line, so that's one residual. Let's say the distance from the data points to the line. Okay, so here you can see that I didn't put all the residuals because the plot would be like a mess, we'll not be able to figure out anything. But here I include some of the residuals. So the first thing that we're gonna do is, I'm gonna find the errors that we make using that line. Now, I don't really care if the error is below if the error is negative or if the error is positive. So in other words, I don't care if the data point is below the line or if the point is above the line. What I really care, if I want to summarize, is I want the line that is the closest one to all the points. Either it's above or below, that's not important. What I care is about the distance, the magnitude of that distance. And that's why what we're doing, because you don't care if the residuals are positive or negative, I usually take the square of the residuals. You can also take the absolute values, but when we're looking for analytical solutions, usually working with squares makes things much easier. So then I'm going to take the square of those distances, I'm going to add them up, and then what I'm going to do is I'm going to try to find the line that minimizes the sum of squares of those distances. Okay? And we denote that by SSE. So basically, what I'm going to do is I'm going to, let's say, play with that line, calculate those errors, sum them, first of all, take the square, let's say find the errors, take the square, sum them up, and then choose the line that is gives you, let's say, the smallest sum of squares of, let's say, those errors. Okay? Now, the good news is that because you have softwares, and because there is also an analytical form for that case, I will not do random trials to find the best line, but we're going to use software to find what is the best available line. But here I'm giving you some examples. So here I'm giving you different combinations for alpha and beta. So let's say here, alpha 700, beta 0, different combinations of the alpha and beta, and then you can also see the sum of squares of the errors. So you can see here, okay, here I got a smaller one, even smaller here, okay, here even smaller sum of squares of the errors. If we modify that line, we get different values for the sum of squares, and our goal is to find the line that minimizes that sum of squares of the errors. Okay. Now, regarding the linear regression, sometimes I may call it linear regression, sometimes we call it, OLS regression, sometimes just a regression. So these are the same names, refers to the same thing. We're talking about trying to find the best available line that can be passed through the data points. Okay, now let's use Excel to try and fit the best available line that can be passed through our data sets. So what I want you to do is go in our folders and then download the Chicago crime data set. I think you can find them on week 1. So that's week 1. And then Chicago crime data set. So let's open the data set. And let's see how can we use Excel to find that best available line. Any questions before we get into Excel? Any questions? Yes.
So could you repeat again what beta represents? I know you said there was like.
Okay, so in mathematics, right? So let me show you. So in mathematics, we have that equation, right? So y equals to alpha plus beta times x, right? So if I have that equation, the alpha represents the y-intercept. Let's say when I have the line, the value, let's say if I have a line, the value that is at y-intercept, the value at x equals to 0, right? So that's the alpha. The alpha is the y-intercept. Basically, for the value of x equal to 0, what's the value of your y? That's for the alpha. Now, what is beta? Beta is our slope. Okay. So what is the slope? The slope is telling you the rate of change of the y, right? But let's think a little bit more, like more careful about the slope. So, okay, the slope will define the steepest of that line, but basically it's telling you the rate of change of the response. So in other words, if I increase, let's say my x by 1 unit, what should I expect to see, what change should I expect to see on my y? If it's a positive number, then I'm expecting to see also an increase. Let's say if I go from 20 to 21, if the slope is positive, so that means I'm expecting to see an increase in the number of crimes. The magnitude of the slope will tell you how many crimes more should I expect. If the slope is negative, then one increase in the number of the x, you're gonna see a decrease in the number of crimes. Okay? And this will be the slope. Yes?
Isn't alpha not always relevant based on where your data lies on the
Yeah, so that's a very good thing, and we're gonna talk about in a minute. So your classmate said, so the alpha may not always be relevant to our analysis, and this comes to the things that we talked, I think, a little bit last time, and we're going to talk today about extrapolation. So usually, if I have a data set and I don't really care much about what happened when x equals to 0, then this may not be of interest. Okay? It may not even make sense, that value for the y-intercept. So usually, our main focus will be on the slope. Okay? And also regarding the slope, it also telling you which variables are significant, but we're going to talk about these in a while. Okay? Any other questions before we go in Excel? Any questions online?
I have a question.
Yes.
What is the difference between intercept term and regression coefficients?
So in our regression model, the alpha and beta are basically the regression coefficients. These are the coefficients that we need to estimate from our regression model. The first one is the alpha. The alpha is called y-intercept. Beta is basically the slope. Okay? So those coefficients are basically the y-intercept and the slope. It's just different ways. So if I want to call these, giving one name, I'm going to call them regression coefficients. But it's nothing else but the y-intercept and the slope. Is that clear?
Yes, thank you.
Yeah. So it's more like a name for the alpha and the beta. So alpha is the intercept and beta is the slope. Okay, now let's go in Excel. Now to do linear regression, to apply the linear model, you need to install some packages, actually one package. So here I have the link. How can I send the link over there? Is that easy? Yeah, but I don't have the chat here. I'm not sure how to move to there. So if you Google actually, load the analysis tool pack in Excel, okay? These should redirect you in that website. And then you have the option for the Windows and for the Mac. So I'm going to show you how you can do it in Mac. But if you have Windows, just Google load the analysis tool pack in Excel. Go in the official website, and this will help you. I will give you the steps that you need to follow to apply, to install that package that we need in Excel in order to apply linear regression.
And your slides are in week, are you still in week 1 or are you in week 2?
My slides are in week 2.
Okay, the slides are in week 2, so they can look at that if they're trying to do this while you're talking.
Yes.
Okay.
Yes, definitely. Yeah. I have those slides. I already upload them
Okay.
under week 2.
Perfect,
Yeah.
perfect.
Now, let me show you how to install the package before we go and do that, apply the linear regression in Excel. Okay, so we're here. So you go to the tools, okay? So you open Excel, you go to the tools, and then you go Excel add in, and then you need to basically install, click here on the analysis toolpack, and then you click OK. Basically, that's it. This will tell Excel that we're going to use some of the tools that are in that toolpack. Okay? Now, how do we apply the linear regression? So here I have the temperature. I also have the crimes. Now, what you have to do, you need to go to the Data tab. So go Data, and then Data Analysis. And then here you can see different options. So we need to choose the regression. You click OK. And then you need to, for the first range there, the input Y range, you need to choose your dependent variable, so your response variable. So in this case, it's basically the number of crimes. So go and manually choose the data set in Excel. We choose that column. Okay. So let's choose them. Okay, we're here. Okay. Then input the X range. Here you need to tell Excel where can it finds our independent variables. So basically our X. So here is the temperature. So you go and you choose the temperature with the column with the temperatures. Okay. So let them choose. Okay. Okay. We choose them. Now, one thing that I need to be careful regarding Excel. So you can see that in our data set, the first row is basically the names of the columns, right? So here I have the year, month, day, temperature, crimes. So I want to tell Excel that, don't consider the first column in your linear regression because these are strings, right? These are characters. So I don't want to take these into our analysis. So you need to click the labels here. This is telling Excel that the first row is basically the names of the columns. Okay. Then you choose here the new worksheet, and then you click OK. Okay. Now Excel will give you the following output. So in today's lecture, we're going to try to talk about a lot of things in that output, but for the time being, I want you to just focus on this part, okay? The coefficients. So actually, maybe zoom it a little bit. Okay, so here we can see in that table, you see the intercept, you can see the temperature, and then you have some coefficients. Now this coefficient is basically our alpha. That's the coefficient, that's the y-intercept. And then the coefficients for the temperature, this is our beta, this is our slope. So in other words here, Excel is giving you the regression coefficient. So our model here will be y equals to the y-intercept. So here it's 560, let's say 7, plus the slope. Actually, let's use some decimals here. Maybe, let's say 0.28. And then I have 3.11 times x. So basically, this is our linear equation. That's the equation of the best available line that can be passed through our data points. And actually, that's not far away from our fourth example. So the fourth example here was basically 567, and the slope was 3. Here, the actual ones was 567.28 and 3.11. So we're actually quite close to the best available line that can be passed through the data points. Now, what I want you to do is let's do some practice. So I want you to repeat the same calculations, the same things, using the Chicago crime data set, but I also want you to access another data set. That's the data set that you can find in week 2. So that's the voters turnout 16 to 68. So that you can find them in week 2. So what I want you to do is open also that data set. Here I have the age and also the rate of turnout on the elections. And again, I want you to feed the linear regression. Let's say I want to use the age to be able to see if I'm able to predict, let's say, the rate of turnout on the elections. So let's do this practice. So 2 data sets, the Chicago data crime and also the voters turnout. Actually, I didn't open the correct one. I want the voter turnout 1868. Okay, so that's the data set. You can find them under week 2. And then let's do some practice. And I will go around to see if you have any questions regarding the linear regression in Excel. Okay, so I'll give 2 minutes. So if you have any questions online, feel free to ask me. We're able to install it then. Okay. So the data set is the voters turnout 1868. That's under week 2. The first data set in week 1. So let's find the equation of the best available line for these 2 data sets. For the were you able to?
Yeah,
Okay.
I got it.
Okay, that's good. Also, for the voters turnout, you can create a scatter plot, right? We know how to create a scatter plot, and indeed see that, okay, there is a linear relationship between the variables. So you have those skills from last time. So we get a data set, we can create a scatter plot. Okay, and now we add one extra thing, which is if the relationship is linear, we can feed that best available line that can be passed through the data points. Few more minutes. Any questions? And I can also remind you, let's say in the last class, how do we create a scatter plot, right? So we choose our data set. And then we went in the insert, scatter plot, click enter, and these will create a scatter plot, right? For the temperature versus the number of crimes. You can do the same thing for the age versus the rate of turnout, right? You choose the data set, You go insert, here in the scatter plot, you click, and then you can see the relationship between the age and the rate of turnout. And as you can see, that's like a linear relationship, right? Between the age and the rate of turnout in the elections. Now, I also want to remind you, let's go in the Chicago crime data set. So we know what's the equation, right? It's y equals to 567, roughly speaking, plus 3 times x. In our scatter plot, if I want to visualize the linear regression, what I can do is I can click in one of those data points, right click, and then add trade line. If you click add trade line, then Excel will add the straight line, the linear regression. So you can see here the linear regression in our data set.
Can you show that one more time?
Yes. So let's say you have your, actually let's do it in the voters here. So you click on some of the data points, maybe one of the data point, and then right click, then add trend line, and now these will add the linear regression, the best available line that can be passed to the data points. Okay, can someone tell me what is the equation of the linear regression for the age versus turnout? So what is the value of the y-intercept? What is the value for the slope? Actually, I want someone online. So what are the regression coefficients in the setting where I have the age versus the rate of turnout? Someone online?
Yeah, I have it as
Okay.
y equals negative 0.141 about.
1.414.
Oh, I'm sorry. 0.141, and this is a negative 0.141.
So it's 0.141.
Yes,
Something
sir.
like that. Okay.
Mhm.
Plus, and what was the slope?
The other one should be 0.01, let's say 1 times x.
Okay. Do you agree? So that's the equation. Let me zoom it. That's the equation that you find. So we can see that I have a positive linear relationship between the variables. I have our slope here. This is telling you the rate of change. I have the y-intercept. Now let me go on the slides. So to talk a little bit more about that age versus turnout. Here I have a take-home activity. So I suggest if it's your first time seeing the linear regression, that's a very good practice to see if you're able to find the best available line that can be passed through the data points. Here, basically they give you some data sets, and then somehow manually you need to decide about the best available line, and then you can choose the regression line. You can see how close you are, how far away you are from the best available line, and it also gives you, for the line that you choose, what were the slope, what were the intercept, and what was the sum of squares of the errors. Okay, that's a nice activity, and there are different tasks there, so you can do some practice regarding the linear regression. Okay, now let's go in our data set. So I have the voters, turnout versus the age. So in other words, I want to see what's the relationship between the age and the rate of turnout in an election. The first thing that we always do is visualize the relationship. How can I do it? I have two quantitative variables. I can construct a scatter plot, and this is what we did in Excel. So we constructed a scatter plot. What do we observe from the scatter plot? We see that there is a positive linear relationship between the age and the turnout, right? Now we also find the equation of the best available line. We don't just want to describe the relationship. I also want to be able to go one step ahead and summarize the relationship. So we fit a straight line, right? And then we also find the equation of the best available line, the linear regression equation. Okay, now let's see. Let's try to understand a little bit more for that specific data set. So I got an intercept of minus 0.1408. Does it make sense? So what is the y-intercept? The y-intercept is the value of the response when x equal to 0, right? So this is telling you that when someone is 0 years old, then the rate of change, the rate of turnout in an election is basically minus 0.14. Is that a problem? Does it make sense? Does it matter?
The person isn't born, then they're not gonna vote, so.
And also we know that you need to be active in the US at least 18, right, to vote. So theoretically speaking, I don't really care what happened below the age of 18, right? So that it's not important for us. So that relationship, that coefficient here is negative, but it does not really matter. It's not a problem because I will not really try to predict someone that is not born yet what if they're gonna vote or not, right? So this does not make sense. So I don't really care about that y-intercept so much, and I'm not really worried about that y-intercept. Now, what about the slope? Can someone help me to interpret the slope? So what does it mean that the slope is 0.0104? Yes.
You could say that for every year older someone gets, we would expect their voter turnout to increase by like
That value of the slope,
1.04%.
right? Okay. So how do we interpret the slope? If I increase the age by 1 year, if I increase my explanatory variable, or let's say my independent variable by 1 unit, then I'm expecting to see an increase in my dependent variable by the value of the slope. And in this case, if I increase one age, I'm expecting so much increase. And why are we talking about increase? Because it's a positive. If it was the slope is negative, then I should expect to see a downward trend, and this will tell you if you increase age, you're going to see decrease by that rate for the rate of turnout at the elections. Does it make sense? Now I want you to use that regression line, and another thing that I want you to observe that here I'm using the hat, right? Because that's not the theoretical model, that's the line that I'm feeding in the data set. So that's why I'm using the y hat. Now what I want you to do is tell me what's the predicted rate of turnout for someone that is 31 years old. So in other words, I'm telling you that x equals to 31. What is the expected or the predicted rate of turnout? So I'm 31 here, so I want to go up and see what is the expected or the predicted rate of turnout. And you can use Excel, right? You have the model, just plug in the numbers, and can someone tell me what's the expected rate of turnout? Okay, someone actually already said in the chat, 0.1816. Right? You plug in the values, and this will give you the expected rate. Okay? Basically, that's how we predict. So I have the relationship, I feed the straight line, and then I can use the regression line, the line that summarizes the data set to make predictions. Let's say for the 31, plug in the 31, and this will give you the value. Of course, we know that that's the value of the response, the value of the dependent variable, using the model, using our linear regression model. We can also talk about the residual. How do you find the residual? So basically the residual is the difference between the actual value in the data set minus the predicted. So in this case, it happened to have the value for the 31 years old. That was the rate of turnout on the elections for 31 years old. You get the difference between the actual value and the predicted, and this will give you the error. And as you can see here, we're doing a quite good job, right? Predicting the rate of turnout to 31 years old. Any questions? Now, what we did here is what we call interpolation. So I have some data points, and then I want to predict for a value between the data sets, within the range. Let me tell you something somehow different. Within the range of the values, right? I want to make predictions within the range of our values. Okay? And in this case, actually, we did a pretty good job predicting the rate of turnout. Now, what I want you to do is, let's do maybe the next activity. So that's a take-home activity. So you can see this data set again on the week 1, the slides of the first week. That was the extra activity. That's the data set that I used for the extra activity that I asked you to do. So now actually, let's start talking a little bit about this data set. And maybe let's do a little bit of more practice regarding the data set. Now the Capitol Hill data set contains the square footage and assessed values for 50 houses in the Capitol Hill neighborhood of Seattle. Okay? So I have some data sets from Seattle. I have information about different houses, and then I have the square footage and also the values of those 50 houses. Now, what I want you to do is, I want you to go in week 1, download the Capitol Hill dataset, open them in Excel, and then let's do some practice. So in other words, just follow the directions in that activity. And this is how you need to do it when you're home, right? When you do some practice, you open the Excel file, you have the activity, and then you just trying to see if you're able to implement and do all these steps. Okay? So what I want you to do is basically, I have the square footage, I have the actual price. First, create a scatter plot, then feed the linear regression, and then I'm also asking you to make a prediction using the linear model. I will give you a few minutes. Let's start working on that take-home activity so you can have an idea of how you can do these activities at home.
So maybe after.
Okay, sure. Okay, yeah, sure. Okay, you can find the data set under week 1. Let me also start actually doing it together. So let me zoom it. So first of all, I want to make a scatter plot, right? So I want to see what's the relationship between the square feet and the actual price. Now, if you remember, in Excel, for the scatter plot, the first column will get on the x-axis. The second column will come on the y-axis. So what I have to do is, if I want to use the square footage, let's say to predict the actual price, what I need to do is I need to copy those columns. First, I need to have my x, and then I need to have my y's. Yeah. So I copy paste those 2 columns. Then let's say I want to create a scatter plot. You go insert, you choose here the scatter plot. So these will give you the scatter plot for the relationship. So what do we observe? So what's the relationship between the square footage and the actual value of the house. So what's that relationship? What can you tell me about the relationship?
I think you have an answer online.
Okay, someone says positive slope, yes. So we see that upward trend, right? There is an upward trend between these two variables. That's good. Is it linear? Somehow linear, right? I will almost never have like a perfect linear relationship between the variables. But if I see that the rate of change is somehow constant as I'm increasing, let's say, my x values, then I can use the linear regression. So yes, we can say, roughly speaking, I have a positive linear relationship between the variables. Once you detect the relationship, then we can just feed the straight line, right? Feed the linear regression. How can we do this one? So you need to go in the data part. So you go data, data analysis, regression, click OK. The first one, here you need to choose your response, the dependent. Here I want to estimate the actual price. Then this will be the independent variable, the variable that I want to see how it affects my dependent. So here is basically the square footage. Okay. Again, the first row has the names of the columns, so you really need to click that labels so that you can tell Excel that you know the first row are basically the names of the columns. You click OK, and then you get the following output, and now you have the equation of the linear regression. That's y equals to the y, the alpha, that's the alpha, the coefficient. That's 4.832, let's say roughly speaking, plus then the slope times x. Okay. Again, from the equation of the linear regression, we can see that the slope is positive. So this is telling us that indeed the relationship between the two variables is positive. That's why I see that basically the upward trend. And then I can also have the rate of change of the response and also the y-intercept. Any questions?
How did you get to regression from data on the Excel spreadsheet?
Yes. Let's say how you apply the regression, you said?
Yeah.
Yes. So you go in the data. So you see that data part here, the tab. You click data.
Yes.
And then you go data analysis. Okay. Here are the different methods. You choose the regression. You click OK. Input Y range. Here you're going to choose your dependent variable. So here I'm choosing the observations in the column A. And actually you can do manual, right? So if I delete this one, then I go with my sensor and basically choose the data set. I choose my response. And then I do the same thing for my independent. So let's say square footage. You choose them. You click the labels because the first row it has the names of the variables. And you click OK. And this will give you the output. Is that clear?
It is, but I just don't have that option showing up on my
Yes, so this
Excel.
is what I said at the beginning. You need to install a package. Do you have a Mac or do you have a Windows?
I have a Windows, and then
Yeah, so-
I thought I did install it, but
So that's
for
the
some
step
reason.
that you need to follow. So make sure that you install the analysis toolpack. If you install the analysis toolpack, then in the data part here, you should be able to see the data analysis tab. So can you see the data analysis tab here?
No, I can't.
So
Maybe
it
I
means
should
you
try
didn't
again.
install the package. So try again the steps. For the Mac, I can tell, I know it's like you go Tools, Excel adds in, and then you click, and then these give you that option. For the Windows, please follow these steps. We're gonna make a break like 10 minutes, so please follow these steps and let me know if you're able to install the tool pack. Okay, someone said, can we select columns F and G instead of A and B? It depends what's the relationship that you want to investigate, right? Let me see, what is G and F? Oh, you mean, yes, you can choose FG. Yes, the same data set. You can either choose the FG or the A or B. It doesn't matter. These columns, they have the same data sets. The only reason why I copy the data sets is that when we want to construct a schedule plot in Excel, the first variable that, let's say the first column will get into our x-axis, the second column will go in our y-axis. And in this case, I want my x-axis to be the square footage and the y-axis to be the actual price. So that's why I copy paste those columns. But yes, you can use the column F and G to run the regression. These columns, A and B, have the same data as F and G. So we're gonna make a break like 10 minutes and we're gonna reconvene. So if you have any issues with installing Excel, feel free to ask me now, okay? So we can see if we're able to make it work. Yeah.
And I think during the break would be a really great time to talk to your classmates in your location and see if you can find people to work with for your mock data jam project. This is a great time to do it and take a break.
So any questions for me? The things that we've covered so far. Do they make sense? Do you feel comfortable doing those kind of... Okay, it takes time. You need some practice. So that's why I'm giving you different data sets. So you can play around. Of course, feel free to reach out anytime. Let's say you practice with Excel, you face some issues, feel free to email me, okay? And I'm more than happy to help you try to figure it out and clarify anything that you may have. Same for the PED students, but also for the people that from other universities. So if you have any questions or anything that you want to clarify on the materials that you are covering, on the data sets, on the data analysis, feel free to email me, okay? So I'm more than happy to answer any questions. Okay, now let's go back to our turnout scenario. Okay, so I have my data sets. Okay, we said it's a linear relationship. That's great. I feed a straight line. I made the predictions for the 31 years old. Now let's try to make a prediction for someone that is 78 years old. Okay. Again, using my linear regression, I just plug in x equals to 78. That's a way to make predictions. And then I go to my predicted rate of change to be, rate of turnout to be 0.6731. Now, anytime we're making predictions outside of the range of the data, we need to be very careful. We don't really know what's going on outside of the range. And actually in this scenario, indeed, if you have the data set, let's say from 68 to, I don't know, up to 80 something years old, so here I have some extra data sets, we're gonna see that our prediction for the 78 years old actually is quite bad. So 78 years old, so you're somewhere here, the actual value is somewhere here, maybe it's, I don't know, 0.5, but what we predict was somewhere over here, like 0.67, like very different to what is actually the actual value of the rate of the turnout for the 78 years old. So this is telling us that we need to be very careful anytime we're trying to predict outside of the range of the data. Usually we avoid the extrapolation. We try to restrict ourselves and use the range of the data set that we have to make predictions. I don't know what happened below the smaller value. I don't know what happened above the largest value. I have no idea how the relationship will change. And this makes sense, right? In reality, let's say above 68 or something, then people, they may not go, they may have, I don't know, other issues that they prevent them, right, from going too low. So then it makes sense to, okay, I see an increase, and then after that age, maybe I see some decrease on the rate of turnover in the elections. Okay, so we need to be careful anytime we are predicting outside of the range of the data. Another question that I have for you is, can we still apply the linear regression? So now let's say you have the whole data set, right? You have from 18 to 80 something. Can you still apply the linear regression? Why not, right? Yes.
I mean, you can literally apply it, but it won't be accurate anymore.
So the thing about statistics and the statistics tool is that, yes, you can apply them in any setting. But the problem is, do they make sense? Or are they going to give us any meaningful conclusions if you apply those tools? Yes, you can apply the linear regression here. You can feed the line. What you can gain from that one, okay, I can see it's a positive relationship. Maybe the slope can tell us that it's, because the slope is a positive, I can get that idea that, okay, I have a positive relationship. But should I really trust the results from that one? Someone is talking online. Chat. Okay. So, a strong correlation. Yes. So in this case, because we see that curve, right? Someone said on the chat it's a curve relationship, right? So applying the linear model may not be the best idea, right? Yes, you can apply the linear regression, but should we trust the results from the linear regression? Maybe no. We need to be cautious about that one. But what we can do, let's say, what are the approaches that we can follow anytime we see a trend that is not linear? There are different ways to handle those issues. There are a few easy ways, and there are some more complex ways to do it. The first one is try to rescale your variables. You know, sometimes by taking maybe the logarithm of one or both of the variables, or taking the square root of the variables, or taking some inverse of those variables, maybe they will make the relationship to be linear. Okay? So you apply some kind of transformation to the variables, and then you apply the linear regression to the transformed variables, right? But you need to be careful. Now we're talking about the transformed. Let's say maybe I'm talking about the logarithm of the age versus the rate of turnout. Okay? But I can still, if I am able to get the linear regression, so the linear relationship, I can use the linear regression and make conclusions based on that linear regression. Now, another thing, another quick, let's say, method that we can apply is that, okay, I have this data set, right? I know from 18 to 68 is kind of linear. Then maybe it's linear here from 68 to maybe 80, but with the negative slope. And then again, kind of a linear from 80 to 80 something. So what I can do is I can split my data into different parts and then apply linear regression in those parts. Let's say maybe apply linear regression in this part, linear regression here, linear regression that one. That's one way to do it. Or alternatively, you can use what we call the polynomial regression. And this is what I'm going to show you here. So this one, instead of just having, let's say, the turnout and the age, because I see the curve, right? I see curve relationship between the variables. What about I just include different transformations of the data, or of the variables, of the independent variable. Instead of just considering the age, I can also consider the age to the power of 2, right? Or the age to the power of 3. I can make the model a little bit more complicated so that I can be able to hopefully capture the curve relationship between the variables. And this is what I'm doing here in those examples. And I'm going to show you in a minute how we can do in Excel. So here you can see if I add the quadratic term in our linear model, I have the age, I have the age square. Then here you can see what is our model, the regression model here. If I add the third order, I get the age square, h to the power of 3. Then you can see that our regression will be like this. And similarly to the fourth, and let's say if I take up to the 10th order polynomial. Now, which one do you think is the best? You said, which one?
Last one?
Okay, so here you said, okay, I see in the 10th order that my line really follows the data points, right? So maybe that's a good idea to use the 10th order. Regarding the regression, we need to be careful to not what you call overfit the data. So we are using the regression line or the curve in this case to summarize, right, the general pattern. I don't want to get into a situation where my line is exactly following the data points, the trend of the data points, because in this case, I'm not really capturing the trend, I'm just following the data points. So it's always important to be careful about adding more terms in the model and also try to not, so be careful about, be cautious adding more terms in the model and also whether it captures the real pattern of the data or you just basically follow the noise in the data, okay? So there's a trade-off between the number, let's say, of polynomials that you're gonna add and let's say the simplicity also of the model. Okay, another comment that I want to make about this is that anytime you add more terms in your model, it makes the model much more complicated, which means that it's much harder to interpret what are these regression coefficients. So before I had the y-intercept, I had the slope. Now if I go to the 4th order, then those coefficients, it may not be that easy to interpret. What do they mean? What is the coefficient in front of the x to the power of 10? It makes things much more complicated also regarding the interpretation. Okay? So I have, okay, the complexity of the model. I also have to take into account the interpretation of the model. So we need a model, so there's a trade-off between that simplicity and overfitting. So usually we try to find a balance. I want a model as simple as possible, but I want that model also to capture the underlying trend or relationship between the variables. Okay? So that's a very important thing that we need to pay attention to. Now, how can we perform those polynomial regression in Excel? Let's go in the voters turnout. Okay, that's not the correct. So I want the voters turnout. Let's say I want all the data set. So I call it voters turnout. Okay, let's open them in Excel. Okay, so let's create a scatter plot. Insert. Let me maybe increase here. Okay, so let's create a scatter plot. Okay, so now we can see that curve relationship between the variables. Now let's fit the straight line. So a quick way is add the trend line. Add the trend line. That's the linear. Okay. Now if I want to add the actually I can also display the equation. So you see here it says display equation on the chart. If you click, it's basically showing you the equation. Here there's also the option of polynomial. If you click polynomial, then you can decide, you can choose about the order of the polynomial. So that's the 2nd order polynomial. And actually let me display the equation here. So here you can see what is the equation. Let me make it bigger.
Maybe you can just expand the whole thing.
I will just zoom it.
Yeah.
Yes. So here you can see what is the equation of the 2nd order. So you can see that I have a regression coefficient, x squared plus another coefficient here, that's the slope, times x minus the intercept. The order does not really matter. Okay, it's the same thing, right? Even if I put the y-intercept first or the 1st order or the 2nd order. Similarly, you can increase that. So let's do the trade again. Add trend line, polynomial, let's say maybe add 4th. Okay, now you can see that it adds. Actually, I want to delete the 2nd one. Let me delete this one. Now you can see that Excel, let me show you again one more time. So click on the data points, right click on the data points, right click, add trend line, and then here polynomial, number 4, you want, let's say, the 4th order polynomial. You can also display the equation, and this will give you both the line and the equation of the best available line that can be passed to the data points if you want to use, let's say, the square, the cubes, and also the fourth power of Rx. Okay, so simple, and then you can feed different polynomial models. Any questions regarding the polynomial?
Like, can you do it again? Because mine didn't change.
Yes. So let me delete the previous model and let me do it. So you have your scatter plot, right? Now I want you to right click on the data points. Right click on the data points.
Oh, I think I see the issue. I still have the voter turnout 18 to 68. You just have the.
Okay, that's a different data set. So I have two
Okay.
data sets for voters. I have the data set from 18 to 68, and then I have another data set on the week 2, which has the full data set for all the range of ages that I have. That's the voters turnout. That's a
Okay,
different
all right.
data set.
All right, thank you.
Yeah, no problem. And then add the trade line, and then you can choose different models that you want to fit. So you also had a question here?
Yes. So the goal of the polynomial trend line, that's just to make as accurate of a prediction as possible?
Is trying to summarize the trend of the data, right? Summarize to not just using straight lines, but now we're talking about curves. The more complicated you make your model, it's gonna follow basically the data points that you have. You don't want this one. The linear regression, the regression is used to summarize the trend, the general trend of the data set. I don't want to go exactly data point by data point, because then if you want to make predictions, you will make mistakes, right? You make big errors in that case. So I want a model that can summarize the relationship, not going exactly through all the data points, but just summarize the general trend of the observation. So this will help us to generalize the model and be able to make more accurate, let's say, predictions. Okay, so similar logic is that instead of just adding polynomials for one variable, what about we can just add more variables? Okay? Not just, let's say, the square, the cube of, let's say, a variable, but what about I can add more variables? So I'm not going to use just the age. Maybe I'm going to use ethnicity. Maybe I'm going to use other variables that they may affect maybe their incomes, some other variables that I may think that they may affect the rate of turnout. And then I can similarly add them into the model, and this will give you what you call the multiple regression. Okay? Now, how do we do that in Excel? So to do the multiple regression, actually let's do the take-home activity. That's the Capitol Hill dataset. Okay, so Capitol Hill dataset. And let's see how do we apply the multiple regression. Now in this dataset, I want you to observe that I have the price of a house, I have the square footage of a house, and I also have the number of bedrooms. Maybe I think that, the price of a house is also affected by not just the square footage, but also how many rooms, how many bedrooms are in that house. So I want to incorporate that information into our model. So in this case, I can, let's say, apply the linear regression. Now what you can do, the first thing is you can create a scatter plot to see the relationship between, let's say, the price and the bedrooms. And then you can basically fit the multiple regression. Now let's see how do we fit the multiple regression. Again, you need to go to the data and then data analysis. You choose your regression. You click OK. And now let's choose our dependent variable. That's our response. So that's the price, let's say. Then I want my independent variables. So let's say in this case, I want the square footage and also the number of bedrooms, the bedrooms. So I choose both of them. Actually, I made a mistake. I need to choose the data, not the whole columns, but the data set. You need to click again the labels, right? Because the first row has the names of the columns. And then let's click OK. Okay, now let's see what we get here. Okay, now I got 3 coefficients. First one is the intercept. So basically our model is y. Let's say I will write maybe, let's say predicted value equals to what? I have the slope, the y-intercept, sorry, the y-intercept. Okay. And then I have the square footage. So what's the coefficient in front of the square footage? Is that 351 times, let's say, the square footage plus, let's say, the number of bedrooms. Okay, here I have a negative minus 26 times, let's say, number bedrooms. Okay, so this is the equation of the model of the regression line. Okay. The value, intercept, and the coefficients for the different variables. And again, why do we need those polynomials? Why do we need the multiple regression? Because if I feel that there are some other variables that they may affect the dependent variable, if I include them, hopefully I can get better predictions for the dependent variable. Okay, so you should let's say improve our predictions for the value, or let's say in this case for the value of the house. Any questions? Yes.
Can I chime in?
Yes, yes.
This is incredibly important. Almost all data jam teams use correlations, and they think one variable is predicting another variable. But once they get into their project, they realize that there are going to be multiple factors that are influencing the outcome. And it would be much, much better to do a multiple regression. But most of the teams don't know how to do this. And most of the teams have teachers that don't know how to do this. So they're going to be really, really dependent on you as mentors to guide them through this. Being able to use an easy program like Excel that allows you to do it more easily than in some other programs will be something that you begin to rely on heavily. One of the most common comments that come from data jam judges when they're judging projects at the very end is, probably you should have used a multiple linear regression to look at this, because there's clearly a number of factors that would influence the measure that you want to look at. So this is extremely relevant to what you'll be doing as a mentor.
Yeah. I got a question online. It says, is there a way to represent all these data on one graph? So here I have 3 variables, right? Before I had 2. Can you think of any ways to represent them? First of all, can we use a scatter plot to represent the relationship between those 3 variables? Not really, right? If I really want to see all of them together in scatter plot. Yes, I can do a scatter plot for, let's say, the value and the number of bedrooms. I can have a scatter plot for the value and the square footage. But all together, yes.
To that point, depending on the software that you're using, you can do a 3D scatter plot.
Exactly. You need 3D plots, okay? So here I have 3 variables, so I need 3 dimensions to represent those variables. So if you have access to software where you can create a 3D plot, then you can use that 3D to represent, let's say, the relationship between these variables. But it's not easy to do that in Excel, to be able to visualize the relationship between the variables. Okay?
I believe it can be done in Tableau. Is that right?
Yep,
I'm
yep,
pretty
yeah.
sure it can. And we have a lot of information in the, on the website about how to use Tableau and a lot of videos to guide students. So if you end up with students that want to do this kind of thing, and hopefully you will end up with more and more, that might be an option for guiding them to something that isn't as hard as it could be.
I also got another question. So it says, could you please explain what this means? Yes. So here, maybe my notation was not ideal. So here, basically what I was trying to do is, I was trying to write the equation of the regression line. Okay, now I have more than one independent variables. Okay, I have, let's say, x1 and maybe x2. Okay, so here what I'm going to do is I'm going to use, let's say, y hat equals, let's say, those values. Let's see if this is going to simplify it. Then I have the coefficient times maybe x1. x1 represents the square footage. And then I can have, again, the coefficient times maybe x2. Now I'm going to name the number of bedrooms as x2. Okay, so these will be your regression line. That's a line that is basically summarizing the trend of the data. Okay? I know it may be not easy to interpret different terms here. Anytime we get into the polynomial regression, anytime we get into the multiple regression, then the interpretation of those coefficients may be a little bit harder, but we can use that model to make predictions, more accurate predictions, let's say about, in this case, about the values of the house. Okay? So this will be our equation. So in order to make predictions, I need to know the value of the square footage of a house and also the number of bedrooms. If I know both of these, then I plug in the values for the x1, for the x2, and then you can get what is the predicted. You have a question here?
Yeah, I might be wrong on this, but there's no way to pull out what weight each variable you put in affects the output.
So you mean the effect of each of the variables in
Yeah,
your
like,
response?
so for example, maybe you have a constant variable that doesn't affect it at all, and you include it in your multiple regression. It'll be included and you'll be able to fit a line, but the degree to which that influences your output.
Yes, so the takeaway is that once you get into more complex models, the interpretation of those coefficients gets much more complicated. You are not really be able to see the effect of different variables to your dependent variable. That's what you are trying to say, right? I guess. So things get much more complicated regarding the interpretation. So that's why I was talking before about the trade-off between the simplicity and let's say, yes, the simplicity of the model. These are more interpretable. We're able to interpret the model compared to more complex model where they may capture the relationship between your variables, but it will be harder to interpret the model. So there's always a trade-off in statistics and all those different models, simplicity versus, let's say, overfitting the data. So these are like, yes.
I think you have a question.
Yes. I believe that SQRT was supposed to be SQFT. Yes, sorry. That's FT, square footage, okay? And then this is the endness and conjunctivity. I don't believe these would be required in this course, right? I'm not sure what do you mean by conjunctivity. Can you please elaborate? What do you mean by conjunctivity?
Oh, I was just referring to, the last question someone had about being able to derive how much effect one variable has on another.
Oh, I see.
We're going to be able to get into it in that detail.
Okay. Any other questions? Okay. Now, let me briefly get into some metrics regarding the linear regression. Now, theoretically speaking, there are a lot of what we call diagnostics. So are some, sensor, yes. So there are some tools that we can check to see, that we can create, that we can utilize them to see if indeed the linear model was a suitable model for our data set. Okay? So for the people that they took some stats class before, they may have heard of residual versus the fitted value plots, normal QQ plots, all those different residuals, all those different diagnostics will help us to decide about, let's say, how appropriate is our model, and if indeed the linear regression fits the data set. But these are, I feel, are out of the scope of this class. So what I'm gonna tell you here is about some metrics. Some metrics that, again, they can give you an indicator whether or not you did a good job with your linear regression. So the first one is what we call the R-squared. Okay? The R-squared describes the percentage of variability in the response that is explained by the predictor. So the R-squared is nothing else but the square of your correlation. So the R-squared is a good measure to see, let's say, measure the linear relationship between the variables. So it's R correlation to the power of 2. So I'm taking the square again. It's kind of, I don't care if it's a positive or negative. I just want to see how strong is that relationship. So higher R square is an indicator of a strong linear relationship. And the higher the R square, it means that you have a better fit of your linear regression to a model. Here we need to be a little bit careful. R square increases as we are adding more and more terms to the linear model. Okay? So yes, I want a large R square, but if it's too large, maybe you should be careful about maybe overfitting the data. Okay? Because as I add more values in the model, the R square will always be increasing. So here there is like an adjusted metric, so it's called adjusted R square. So the adjusted R square is basically controlling for the number of variables that you're adding in the model. So sometimes we look, let's say, the adjusted R square, but again, the R square is an indicator about how good fit is your model to the data. Okay? The second one is what we call the residual standard error. Okay? So that describes the size of a typical residual. Okay? So what is the residual standard error? Is nothing else but the standard deviation of your residuals, right? You remember what are the residuals? It's basically the error that you make. Of course, the smaller your error, then the better job you're doing, right? So these may also be an indicator that you can look to see how good job you're doing in those specific data set. Okay? We need to be, again, a little bit concerned, a little bit careful about the residual standard error, because that depends on the magnitude of the values. So let's say if you have different models, different data set, it may be very hard to compare them across. But these will give you an idea, let's say, of how good fit you have, again, to the data set. So the smallest the residual standard error, the better fit we have in the data set. And then I have the residual, the standard error of the slope. This describes how much variability exists in the estimates of the slope coefficients. Okay, so what is this one? So in the linear regression, we are estimating the slope, right, that beta. I don't know what's the value of beta, and I'm estimating them. So the standard error of the slope is basically telling you what's the standard deviation of those estimates. As you can imagine, the smallest the standard deviation, it means the more accurate are our estimates for the beta. So the smallest values, or smaller values of the standard error of the slope, that's an indicator that our estimators for the beta are better, okay, are better. The smaller the value, we're doing a better job at estimating that beta. So they're more stable, okay, more stable and more accurate. So that's like another metric that you can use to test, let's say, the quality, the feed of your model to the data. Okay. How can we get this information? The good news is that softwares can give us those kind of information. So here I included the output that you get in Excel. So here I have the outputs from the crime versus the temperature, the first data set that we use. The things that we've covered so far. So let me use a highlighter. So we talk about the intercept, the coefficient here, right? That was the alpha hat, the estimation for the y-intercept. We talk about the slope, that's the beta. Okay. Now we also add some more information. Now we know what is the R square. So the R square is that metric that I told you before. The larger the R square, this is telling us that I have a better feed of your model to the data. Okay. The R square takes values from 0 to 1. Okay. The closer to 1, it means the better feed. Again, be cautious. Adding more variables in your model, we increase the R square. So if the R square is too large, it means maybe you are overfitting the data. Now we also have the adjusted R square. This is a variable where it's somehow controlling for the number of variables that we have in our data set. The multiple R is nothing else but the correlation. So the linear model output also gives you the correlation. That's a correlation. If you take the square of the correlation, this will give you the R square. So the R square is, you take that multiple R square, and this will give you that square. And then I also have the standard error. And then we also talk about the standard error of the slope. Now, how can I find the standard error of the slope? I need to go in that output. So here, this is our slope here, right? The coefficient, the beta. This is an indicator how good job you're doing with that estimate. Okay, that's how spread are the values of the coefficient around that estimate that you have. The smaller the standard error, it means the more accurate our estimator it is, okay, for the slope. Okay. So these are some indicators that you take a look when we're doing linear regression. Sometimes you may apply different models, and then you can look those metrics to get a sense of how good job you are doing with that specific model to feed and describe, let's say, the data set. Okay. And here I have a take-home activity. So I think we don't have enough time to get into that activity. So basically what I'm asking you here to do is you go to the Capitol Hill data set and then calculate, tell me what is the R square, basically run the linear regression, and then how the R square changes if I'm adding the number of bedrooms. So I have two cases, right? I have the value versus the square footage, and then I have another model which is the value versus the square footage and the number of bedrooms. So basically I want you to compare those values, the R square, the residual standard error, and the standard error of the slopes across those two different models, okay? And see for which one you do a better job. Okay? So that's like a take-home activity. Any questions? So any questions online? So I have 10 minutes left, so I want to introduce the topic about the statistical inference, and I'm going to continue my discussion in the next class. So you have a question here? Okay. So let me talk about that general idea that we're using in statistics. So usually we have questions about large populations. Maybe I want to know more information about all the Americans, right? I have large populations. The problem is that in a lot of cases, it may be impractical, it may be impossible to ask all the members of the population. So in our scenario, let's say I want to know something about the Americans. Maybe I want to know their average income, right, of all the Americans. It may be impractical, impossible. It may be costly, time-consuming to go and ask all the members of the population. In some cases, it may be possible. Let's say, how can you really ask all the Americans, right? So in a lot of cases, it may be impossible to even ask all the members of the populations. Then what we're going to do is we're going to get a smaller subset of the population. We're going to call it a sample. So let's say I have my population. That's a large set of objects, subjects, depends what I want to study. And then I'm getting a smaller subset of the population, and I'm going to call it that as a sample. And our goal of the inferential statistics, of the statistical inference, I want to know ways to do the analysis in my sample, but be able to generalize my results to the whole population. Okay? How can I analyze the data from the sample to make the conclusions for the populations? This is our goal in the statistical inference. Okay? And let's see a scenario. So let's say there is an election coming up. Actually, that's true, right? There is an election coming up in the States, right? And I want to know what's the proportion of voters who will vote for Republican or let's say the Democratic candidate, right? Now let's assume that I'm interested to see the proportion of voters that they're gonna vote for the Republican. Okay? Think about it. If I know the proportion of voters that are gonna vote for Republicans, I also know the proportion of people that are gonna vote for the Democratic, right? Because I have just two parties, right? So if I know one proportion, I can also, it's one minus, I can get the other proportion, okay? Now let's say I want to find what is that proportion. Now, as we said, finding the actual proportion, it may be hard. I need to go and ask each one of the Americans what you're gonna vote, right? And then collect the data and take that proportion. That's not practical, right? And then what we're gonna do is, I'm gonna get a smaller subset, and this is what I'm gonna do here. So I'm going to do a poll. Okay? I'm going to poll some people. Okay? I'm going to get a sample of voters, and then I'm going to use that sample to calculate the proportion of people in that sample that they're going to vote, they're going to support the Republicans. And I'm going to denote it by Q hat. Okay? So Q will be my population proportion. We call it estimate. Sometimes we call it the population parameter. That's a parameter. We denote it by Q. And then I'm going to get a sample, and I'm going to calculate the proportion of people inside in that sample, within that sample, and I'm going to denote it by Q hat. And we're going to call it as an estimate. That's an estimate. So Q hat is an estimate of the estimate, of the parameter, of the actual parameter, the actual population parameter. Now let's decompose the estimate. Now here I'm claiming that the estimate will be equal to the estimate, the actual value, plus some bias, plus some noise. And I'm going to explain to you what do we mean by bias, what do we mean by noise. Now the bias is any systematic error that we may do while we are estimating the parameter. So any systematic error that it may occur in the procedure of estimating the parameter. Let me give you some examples. So here I'm doing a poll, right? Maybe I know that when you're conducting polls, maybe people are lying. They're not really saying the truth in that case. So this one will add some kind of bias to your estimates. Or maybe if you're doing the polls, let's say online, right? Again, maybe those people that they are going to vote in those online polls maybe have some specific characteristics, right? And these may not be really representative of the whole population. So maybe these, again, we're going to add some kind of bias to our estimator, okay? So this is what we mean bias. Any systematic error that it may occur while I'm estimating the parameter. Now, what is noise? Noise is nothing else but the natural variability that the data have. So in general, let's say if I get a data set, there is a chance that I'm going to get a weird data set, right? Or I'm going to get a data set that has some variability that I don't expect it. So that's the noise. That's the natural variability that exists in any data sets. Now, in the next class, what we're going to do is we're going to see actually what are the properties of a good estimator. And what will be these properties? We want the estimator to be unbiased and precise. Okay? So let me briefly talk about that unbiased and precise. So unbiased, it means that if I repeat the procedure again and again, okay, the average of the estimates would be close to the actual estimate, to the estimate. So if I repeat the experiment, if I repeat the procedure again and again, okay, I'm getting samples, I'm estimating the estimate, the proportion. If an estimator is unbiased, it means on average, I'm expecting the value, the average value of the estimates to be close to the estimate. What is the precise estimator? Now, precise estimator, again, if I repeat the experiment again and again, if I repeat the procedure again, getting samples and trying to get the estimates for the estimates, now all the estimates will be close to each other. Okay? And let's visualize those things. So the first scenario, so here you can see those lines with those diamonds. This represents the estimates, the actual value. That's our Q, the actual value of the proportion. With those circle ones, I represent the estimates. Let's say I ask some voters, I calculate the proportion, and this is the value of the proportion. I repeat the experiment again with independent samples, and then I get another estimate. Okay? Here you can see the estimate. So in this case, the estimator is what we call biased and imprecise. Why it's biased? It's biased because if you take the average of all those estimates, the average, I'm expecting it to be somewhere maybe here. So it's different than the estimate. Okay? On average, my estimator here is estimating the estimate differently, right? So it's not precise estimation of the Q. Now, why it's imprecise? I know that on average, the estimator gives value somewhere here, but also the values are very spread out. The estimates are very spread out of the average of the estimate. So these make it biased and imprecise. Now let's see the scenario where it's biased but precise. So why it's biased? Because you can see that if I take the average of the estimates, again, maybe somewhere here, this value is different than the estimate. So on average, my estimates are not doing a good job at estimating the unknown population parameter. Is it precise? Yes, because most of the estimates are very close to one another. So here I have a biased but precise estimator. Now let's say a scenario where I have unbiased and imprecise. So here it's unbiased. Why it's unbiased? If I take the average of the estimate, it will be somewhere close to the population parameter. That's what I want to estimate. Why it's imprecise? Because the values are very spread out around the estimate, around your estimate. So they're very spread out. Okay? And then I have the ideal scenario where the estimator, let's say, is unbiased and is precise. So here you can see that on average, all the estimates are giving you a value that is close to the estimate, to the actual population parameter. It's also precise. Why it's precise? Because all the values are very close to one another. Let's say all the estimates are very close to one another. So these make the estimator to be unbiased and precise. Ideally, this is what we want. We want estimators that are unbiased and precise. Now, in statistics, for the people that they took more, advanced classes, you're gonna see that, more simple methods. Usually, they have high bias but low noise. If you have more complex, then you have low bias but high noise. So there's always a trade-off between these two. Sometimes we allow some biases for getting something else, or sometimes we're allowing more noise to gain something else. So there is again a trade-off between the bias and the noise. Ideally, I want both of these to be as small as possible. In practice, that may not be the case. I may not be able, okay, the meeting will terminate in 1 minute. Okay, I think that's all for today. So have a good one and see you next week.
And remember to form your teams. If you have any questions as you're working on your mock data agenda, just email me. I'll get right back to you.
Thank you.
Thank you very much.
Thank you. Have a good day.
Yeah,
Good
you
night.
too.
Yeah. For some stuff.
I can.
Are you?
Oh, yes.
So based on
I'm just
we're
like
getting into
this
some,
week
bias and
particular.
things, this was
Nuts
the
for me,
poster
but
podiatrist.
I actually.
And they had, the team had come to the
I do
conclusion
have time.
that
I've a little
there
bit
was
of
some
time Thursday
inconsistencies.
afternoon.
It was about food
Tomorrow,
poisoning and
have
health
time.
risk, and there
Just put your laptop just so we can see the slides.
yeah, there were some
Yes.
You don't have-
inconsistencies.
Yes.